There we go. Okay, getting started here tonight. And I've got my phone turned up. Might have a little bit of background noise here in a second, just because I want to make sure that my mic's working. I'm glad I checked it because I was sitting on mute there. So I'm going to be streaming continuous distributions, talking about a few problems. I've got a few notes for you. I haven't finished migrating all my stuff into GoodNotes. Haven't had a chance.
Okay, getting started.
Hadn't had a chance this week to do so. However, let's go ahead and get started, and let's talk about normal distributions, and let's talk about a couple of examples. Again, if you're from my face-to-face class, you come on here, just let me know that you're on. And if you have any questions to ask, I can bring you on to ask verbally if you need to, or if you just want to put it in the chat, I can certainly do that as well. Excuse me. All right. Here's just some ideas with the normal curve. So a university reports that freshman SAT scores have a mean of 1050 and a standard deviation of 150. Is a score of 1200 unusual? These are some of the things that we talk about within the normal distribution. How could we determine the percentage of students who scored below 1200? What do we need to put into effect in our school or in our prep program to get this group of students, whoever they are, to do better on the SAT? Why do many real-world variables appear to cluster around an average value? We'll talk about that later. It might not be tonight, but this is a part of my intro notes, some of my essential questions before we get into some of the computational work in this online session. But for example, you've got heights, ACT, SAT scores, as in that opening question. Blood pressure. Blood pressure is an interesting one to me because it just is. IQ scores, manufacturing measurements. Blood pressure, if you think about it just real quick before we move on to the next set, you might have a group of folks who are on medicine that's helping control the blood pressure. So what is an average blood pressure for those folks that are on this particular medicine, that are on no medicines, that are exercising, the whole nine yards? So there's a whole lot of different other factors, and you have to take into consideration to what degree does each one of these affect the average, but that's for later types of correlation discussions. So there we go. All right, just a part of my notes. I'm certainly not doing all of this tonight, but within some of the problems that I do, these will be some of the objectives that we'll be working on. Describe the characteristics of a normal distribution. I typically go through that in every problem. Explain the role of mean and standard deviation. Same thing. Interpret z-scores. Same within the context of the problems. Calculate probabilities using normal distributions. Use technology. We're going to use TI-84 primarily. Find areas under the curve and analyze real-world data using normal models. This is a normal classroom type set of objectives that I have. I'm just transferring my notes into GoodNotes. Not quite there yet for tonight. I'm not doing all that tonight. But within each of these problems, we'll talk about it. So let's talk about a little bit of vocabulary. And the good thing about GoodNotes, I can write right over the top. So it is a symmetric bell-shaped distribution. It's described by its mean and standard deviation. If you remember from discussions in class, that curve goes out to negative infinity on one side, infinity on the other. It continues to go in that direction. It's asymptotic. It does not touch the horizontal, and there is area between that curve and the horizontal all the way to infinity on either side. The negatives that we talk about on here just indicate what it's a measure of position. It's the z-score. It's where we're at with consideration to the mean, which is right dead set center. So the mean is the center of this distribution, and the measure the measure spread for the mean. We've talked about all of these in detail. Again, this is just a carryover of my notes. Probability. Finding the area underneath this normal curve is going to lend itself to helping us find the probability because those are akin. If you find the area, that is the probability. The z-score is the number of standard deviations the value is from the mean. And in a standard normal distribution, as I have outlined here, the mean is 0 and the standard deviation is 1. So this is a standard normal by definition. And we've done plenty of these. We started in class with the empirical rule, talking about the same characteristics I just talked about, talking about probability a little. And now we're into the meat of it. And again, tonight I'm going to go through just a few problems talking about the normal curve and taking that this information into consideration. All right. So let's say that we have, and we're going to go straight into data. We're not going to have a standard curve right out the gate. So let's say that I have a curve that has a mean of 16. We'll go with regular, just whole numbers, and a standard deviation of 4. Okay. For this example, we'll just go with that. So this particular set of data has a mean of 16 and a standard deviation of 4. And the question is, find the probability that an x value will be less than, find the probability that, I lost my train of thought of, chat popped up. Find the probability that any x value that would fall on this particular continuous curve would be less than, let's say, 14. Okay. The first thing I'm going to do, even as a student, if I was a student in the classroom, the first thing I'm going to do is draw a normal curve. Not too shabby for me, although I extend a little far in one direction. It's okay. There we go. So I've got my normal curve that represents this data, just a sketch. So the mean is right here. Well, the mean of this one is 16. If I go out one standard deviation this way, I'm at 20. 2 standard deviations, I'm at 24. 3 standard deviations, I am at 28. If I go 4 back this way, I am at 12. Back 4, I am at 8. And if I go back 4, I'm at 4. So 4, 8, 12, 16, 20, 24, 28. Still just a sketch, but you can at least see where your data falls on this curve. Now, if I want to find what the z-score is at, let's say, the mean, and most of us in class should already know this, but if I needed to derive this, if I need to figure out what the z-score was, what the measure of position was, in other words, how many standard deviations away from the mean we are at the mean, logically 0, then I would use this formula right here. And we derived this in class way back when, so it's just that the z-score equals x subtract the mean divided by the standard deviation. In this case, x is 16. We're going to subtract the mean, which is 16, and divide by 4. Well, that gives us 0 divided by 4, which ultimately gives us 0, but we kind of knew that from our other discussions in class. So there's the middle of the curve right there. When you're at the mean, you're 0 standard deviations away. Okay? So let's do this with the, whoops, I should have left that, but I'll redraw it. Let's do this with the other pieces. Let's go here, 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 and here. We're going to find these z-scores. Again, because I went out one standard deviation each time, it's going to be 1, 2, 3, minus 1, minus 2, minus 3. However, let's just walk through it. Z equals x subtract mu divided by sigma. And I'm going to take this 12. So I've got equals 12 subtract 16 divided by 4. Minus 4 divided by 4 equals minus 1. So we're at minus 1 right there. No problem. I'll do one more and then I'll just write the rest of them in. So let's derive 24. This one. So I've got 24 subtract 16 divided by 4. That's 8 divided by 4 equals 2. So I'm 2 standard deviations away at the data point from the set 24. No problem. The other ones on here are 1 and 3. -2, -3. But understand that in between all of these numbers, there are other numbers. Like we are looking right now, I shouldn't have erased those out. We're looking right now, let me put those back. I got 16, 12, 20, 24, 28. Apologies on that. Got a little ahead of myself. We're looking for the probability. So again, we're up here looking at this, that the probability of x, an x value in this set being, what is the probability of an x value in this set being less than 14? Okay, well, 14 is not at a lattice point kind of z-score. In other words, it's going to fall somewhere in between. So, oops. 14 is going to be, what's going to be right in the middle here? So that's going to be 14. So basically what we are looking at sketch-wise is we are looking at the probability, gosh knows, sorry, that our x value falls between there, that vertical line, and negative infinity. So what is the area between negative infinity and 14? Well, we can't do that for the curve of the data. We have to standardize it, which we started doing, but we have to find the z-score at 14. So I'll go right up here and I will go z equals x minus mu divided by sigma. The x value here is 14. 14 subtract 16 divided by 4. And 14 subtract 16 is minus 2 divided by 4. Trying to see if I got enough room. I'll go down here, minus 0.5. So your z-score down here is minus 0.5. So what we're going to rewrite here and what we're looking at is an equivalent expression. We're not looking at the probability that x is less than 14. We're actually looking at the probability that the z-score is less than negative 0.5. We can use our table that was handed out in class and share it on the Moodle. We can use the calculator. For tonight's demonstrations, I'm going to use the calculator because I think I pulled from the, if I'm not mistaken, in my last stream, I pulled from the table and the calculator. We'll just do the calculator tonight. So here's what we're looking at. We want to know the probability that z is less than negative 0.5. Okay, I'm going to transfer that over here. So I'm looking at the probability that the z-score is less than negative 0.5. Okay. If I'm looking at less than, then I'm going to be looking at the area between negative infinity and negative 0.5. Those are going to be my two extremes. So when I go in the calculator, I'm going to go second. I'll go to the calculator in just a second. I'm going to go second vars. And then I'm going to scroll down. It's just a short scroll in this one. Binomial is further down. Normal is not. So I'm going to go norm CDF for cumulative density function. I want to take into account all of the values between the 2 points. And instead of using negative infinity, which the calculator is not going to know, I could use negative 500,000, negative 500, whatever I want to do. I'm just going to use negative 10. In my class, I just tell the students to use 10 on either side. It's an easy one to remember, and it's far enough out that you're not going to be off out to 4 or 5 significant digits. You'll be the same answer as the rest of us get. So when you go norm CDF, all you're looking for in the syntax that I use is what is the area between the farthest z-score to the left and the farthest z-score to the right. So in other words, I'm using negative 10 for negative infinity, and I've got negative 0.5 from my farthest point to the right. So what's the area between those two? And we'll come back in just a second and see what it is. I'm going to go to the calculator right now. And I go, oops, second vars, scroll down to normal CDF, enter. And again, there's different syntax for this. I stay simple in class because I want you to derive the z-score and then just use the z-scores in that case. So we're going to go from was it -10. The farthest left z-score, because we're going all the way to negative infinity. So -10 to -0.5. Yep, make sure the point's in there. And I get 3085. That's what I'm going to go with. So 3085. So I get 0.3085. So about a 31% probability that a z-score will lie on that side of that number, about 30%. Now, let's go back to our picture. That makes sense, doesn't it? Because if you remember, from the middle back in this symmetrical curve and from the middle this way, it's 50% on this side and it's 50% on this side. So this area right here being 30% makes logical sense because we are not taking into account this, which would give you that extra 20 to get to 50. Hope that logically makes sense. We've been talking about quite a few of these in class. I'm just extending that now. Because in class you can listen to it and say, I got it, and then walk out. You're like, nope, don't have it. So now you can go back to this example if you need to on the practice problems. So there you go. There's example number 1. Let's move on to a second example. I don't think anybody's on. If anybody's on, I would ask for a question. Like one person might be on. So if one person is on, if you have a question, if you're from my class, by all means, chat it up or ask me. I'll send you an invite. You can come in and we can go back and forth. It's no problem. Let's do another. Let's arbitrarily choose some number. So I'm going to go that the mean is 17.12 and that the standard deviation is 1.4. Still not crazy numbers, but a little bit more real world than those integers that I had earlier. Okay. The question to you is, if we reach into this particular set, whatever this population is, and pull out one individual, whether it's a test score or a person, whatever we're representing in context, what is the probability? I don't want to use that color. Time out. What is the probability I don't want to use that either. Gosh, I'm sorry. Dark background's throwing me off just a little bit. What is the probability that the x value will be less than, we'll go 18.77. Okay? Now what we need to do is find an equivalence here. In other words, we're going to go to probability that x is less than 18.77. We don't work with the data. We don't work with the x value in the sense of what we're doing. We convert this to an equivalent expression. The probability that the z-score will be less than some z-score that represents that 18.77 as a measure of position. Okay? Not too shabby. So let me go to yellow. So we need to find, so we have to find the z-score at 18.77, and that's what we'll put up here in the question mark. We'll replace that, then we'll be able to work with it with our calculator for tonight's session. That is a score. I spelled it right there. So the z-score, z is equal to the x value, subtract the mean, divided by sigma, which is standard deviation. The x value in this case is 18.77. Got 18.77. Subtract them. No. Yeah, that's right. Subtract the mean of 17.12. Divided by 1.4. These pesky decimals. All right, 1.1786. 1.1786. How exact do we want to be tonight? I think I'm just going to go out to do 2 decimal places. So I'm going to actually just round that down to 1.18. So there's my z-score. So that is what we're going to replace this with. is 1.18. Now we can work with it. Now we can go back to working with the calculator, and in the syntax that I use, just what is the area between this z-score and this z-score, we can find that probability. So let's go, let me erase this out. We already found that. Okay, and now down here at the bottom, I'm going to go back to, we'll go to pink, and I'm going to go to calculator syntax, and then I'll go to the calculator itself. So I'm going to go second, vars, that's going to take me to distributions. Then I'm going to scroll down to normal CDF. It's going to have an open parenthesis, and since we're still doing less than, I'm going to go from -10, which is my farthest left, and that -10 in this case is representing negative infinity. I'm going to go from -10 to 1.18. -10 to 1.18. Okay? Go up here. I scroll over. Oops. And I go, I'm going to clear that out. Second, vars. Scroll down to normal CDF, enter. And I'm going from -10, comma, to 1.18. Close parentheses. Boom. 0.8809 or 0.881. We'll go with that. Oops. Equals, what was it again? 8809. Either way, we're about 88%. There's about an 88% probability that when I reach into that population to pull one defective part out, or to pull one male out, or to pull one professor out, whatever our context is, that probability of drawing that one out is an 88% chance of it happening, given whatever our continuous random variable represented, which we don't have a context, doing purely computational tonight. All right, we've gone less than. Let's reverse this. As a matter of fact, let's just reverse this particular problem right here. And I'm going to write 0.8809 up here at the top, just so I still have it, because I'm going to erase all this stuff down at the bottom, at least part of it. So I now want to look at, we'll go with green. I now want to look at the probability that the x value, that one chosen, is greater than 18.77. Well, that's going to equal an equivalence. Remember, the z-score at 18.77 remains the same. The z-score is still 1.18 at that particular point on the horizontal. So I've got now the probability that z, instead of being less than, is going to be greater than 1.18. I already found less than 1.18, and I am going all the way to infinity. So all I need to do in this case is very simply subtract from 1, because the total area under the normal curve is 1. I know the area over this side. I need the area on this other side. It represents the remainder of the curve. So I have 1. That's a funky looking 8809. I'm sorry. I got 1 subtract 0.8809. 1 subtract 0.8809. 1191. Which makes sense. There's 88% on one side. There's about 12% on the other side. That's 100%. Okay. We're going to go now and do one that calculates the greater than first. But I just wanted to show you this. And there's different ways of skinning this cat, so to speak. Different ways to move into that normal curve. So let me just move forward here. And let me go into, now we'll just go up. I will set this at the mean is equal to 1.76. Standard deviation is equal to 0.03. Okay, we'll go with a little bit different numbers. Again, not fully real world where it really seems like it's representing something. Still seems kind of integer-ish, but not integers at all. A little bit more difficult to work with. I want to know the probability that the x value with one chosen from that population is greater than 1.779. That's hard to gauge by looking at it because we want to be quite exact. We're going to pretend we're either a rocket scientist shooting to the moon, we want to get there, or a pharmacist, a pharmacist. We don't want to be off on somebody's medicine. So we're going to try to be a little bit more exact with this. So we're looking at the probability that x is greater than 1.779. I'm going to rewrite that here. The equivalence statement for this is going to be the probability that the z-score is greater than whatever the z-score is that represents the measure of position of that 1.779 on the horizontal. So the z-score is the x value, subtract mu, divided by sigma. The x value is 1.779. So you got 1.779 subtract 1.76 divided by 0.03. I'm just going to go 0.63. So there's the z-score. So in the context of this expression that we wrote over here, instead of a question mark representing 1.779 as a z-score, we're going to put the actual z-score. It'll be 0.63. Now we're somewhere where we need to be. Now we can find this area under the curve that represents the probability. And I'm going greater than. So when I go greater than, I'm going from 0.63 all the way to infinity. Well, instead of using infinity, when we're out 10 places, we are definitely far enough out where we will be exact to quite a few decimal places. There's an infinitesimal amount of area, so teeny weeny, it's not going to affect us with our answers in this course, out to at least 5 decimal places. So I'm going to go back to the calculator syntax, which is second vars, scroll down to normal, CDF, and then I'm going to go from left to right. So my leftmost number here is 0.63, comma, which is right above the 7, comma, all the way out to 10. So 0.63 all the way out to 10. All right. Scroll back over. Let me hit clear. Whoops. I'm always trying to do it on the screen. It's over here. Second vars. Scroll down to normal CDF. And I've got 0.63, comma, 10. Enter. 2643. There's the probability. So about a 26% chance that an x value will land greater than 1.779 on the data curve and greater than 0.63 on the z-score. So there you go. So I have covered problems in finding the z-score, finding the probabilities that go all the way to infinity on either side. These are the easier of the cases. Not that the one I'm about to show you is not overly difficult. However, is a little bit different. So actually, let's do this. Let's use the same example since we've already got these arbitrary numbers up here. And I'll just erase off, no problem. And I will do probably the last example that I'm going to do tonight unless somebody comes on from class that has a question during these online office hours. So let's now look at the probability, and I will just go with the z-score. Let's assume that we've already figured out what the z-score is based on the data that we were given. So I'm going to have, what's the probability that a z-score will fall between, and I'm going to put negative 1.2 and 0.7. So on a normal curve, Let's see if I can draw this down here. Not too bad. Not too shabby. So on the normal curve, I've got 0, 1, 2, 3, and that's just the standard that we put down because majority of our data falls there, and we work with empirical rule, the 3 standard deviations on either side, where it's all the way up to almost the entire curve. So we are looking at the situation that has negative 1.2, which is about right there, and 0.7, which is about right there. So we're looking at this area right here. We want to find the area between those two z-scores, and again, this one is negative 1.2. I'll try to write that a little bit better. Sorry. Negative 1.2 and then 0.7. Okay. Find the area between those two. All right. So second vars, this is using the TI-84, TI-83 or 4. Second vars, normal CDF, and remember the syntax that I use is very simple. What is the area between this z-score and this z-score? So we're going to go with, I'm going to read it. We're going to go with normal CDF. The leftmost z-score, which is negative 1.2, comma, and then the rightmost z-score. Find the area between those two is 0.7. Negative 1.2 and 0.7. So back to the calculator. We'll clear that out. I'll go second, clear, second vars, normal CDF, and I'm going to go negative 1.2, comma, 7, comma. And before I figure what this is, let me just try to guesstimate what it is. If I went between 1 and 1, then the area would be 68%. So I've cut some of that out. In other words, now I'm logically trying to deduce what it might be. I've cut some of that out. So I've cut that out, and I have added that. So in other words, I've taken away that and added that. Now, this is just a half-drawn sketch in all honesty. But looking at this, I've added about as much as I've taken away. However, that's on the lower side of the curve, so I have more of a dip on that side. So the empirical rule said that between 1 and negative 1 is 0.68. This looks like it's about 0.68, but I'm going to say that it's less because we're taking away more. So I'm going to say about 0.54. I'm just going to guesstimate. They're certainly not going to be 0.68. And nobody even saw me do that. I'm sorry. There it is. I was drawing it out. So my estimate, just logically looking at it, is going to be about 0.54. These are arbitrary numbers I made up, so I don't know the answer up front. So I hit enter. 0.88. Daggone, Mike, you were way off. So I was taking away 0.3, which is okay. Again, this was a sketch, so forget I even said anything about that. Not even in the realm. Okay, so 0.88 is actually more. So we're at 0.7, which is not quite at 1, and we're at negative 1.2. I still stand by I thought it would be a little bit less, but logically I was off. It's okay, it's a good place to stop. So anyway, so what I did tonight was I just went through a few examples using the calculator. I went through some where you're finding the area under the curve all the way to negative infinity. I did some where I'm finding the area all the way to infinity. And I did one right here that we're finding the area between two distinct points, two distinct z-scores. Even if they were data values, we could have changed them and then looked at the z-scores, and that's how we would have used the TI-84 in that case. Now in class, we're also using our table There's different ways to look at it. You can also logically look at it. I was off on that. I'm going to have to go back and look at it again, but you could logically look at it based on the empirical rule and have a good eyeball shot of it. Mine was not a good one, but that's okay. So none of my students came on tonight. It's okay. I'm going to post this as a video on demand on my Moodle site for you. It's always on my YouTube site, so you can come back here and at least review what I talked about. Don't forget, my face-to-face class has a quiz on Wednesday on all the formulas from normal distributions, all the definitions from normal distributions. Be able to regurgitate that back onto the quiz. I need you to study those terms that we've been working with and those formulas we've been working with, so you can add them to your brain. All right, that's all I've got for tonight. I appreciate you coming to my stream. I appreciate you stopping by, anybody that did. And I will be back on Thursday night. I will see my face-to-face class tomorrow night. All right, take care. Thanks.